Today we're first of all going to have a go at making pyridine hydrochloride. We've read that this might be able to be used as a demethylating agent for vanillin, and so far our experiments here have failed, so we're willing to try anything. You can make pyridine hydrochloride by bubbling dry HCl gas through an ether solution of pyridine. However, we wanted to have a play and see if we can do it in a less exotic way. So we're starting off here with 20 grams of liquid pyridine. It smells pretty bad and it's toxic, so you want to be careful when handling it and don't spill any. We're going to make our salt the simplest and most hardcore way. So we'll need an ice bath to keep the mixture cool. So let's get the flask set up in there and we'll get the pyridine chilling down. Now we're going to place an addition funnel on top of the flask. To convert our pyridine to the hydrochloride salt, we're going to drip in concentrated hydrochloric acid. So here's 20 ml of 36% concentrated hydrochloric acid. This should be approximately enough to convert all the pyridine into the hydrochloride salt. Like a bloodhound on the scent, the acid is getting pretty frisky and excited. It just knows there's some tasty amine somewhere nearby to react with. Let's get it in the funnel. Okay, so all systems are now go and we're ready for lift off. So let's open up the addition funnel and see what happens. We have main engine start. A thick fog is produced in the flask, but there's no sound and no sign of a violent reaction. And there we go. It was over pretty quickly and painlessly in the end. The flask is warm, so we'll let it cool and then remove it from the ice bath. Here's the resulting solution. It's an incredibly bright looking liquid. It must have some special high refractive index because it looks a bit like liquid diamond. Let's check the pH. Well, it's coming out as slightly acid, but the mixture still smells slightly of freebase pyridine. So we added a little more hydrochloric acid carefully until the aroma of pyridine disappeared. And at this point there was no more smoke produced when hydrochloric acid came near. Here we go. Looks about the same as before. Just slightly acid. So perhaps this is normal for this particular salt. Well, this mixture now has water in, and so our next challenge is to see if we can remove this, or at least as much as we can. So we placed it into a beaker and had a go at reducing down on a hot plate. When the liquid reduced a bit, we transferred to a glass petri dish and continued to heat. Soon the entire room filled with white fumes, and we realized that we were probably evaporating more of the actual product than water, so we stopped heating and allowed to cool. Here's the result after chilling: a petri dish full of ice like crystals. But it's not completely dry, and on warming slightly there's some liquid in here. But there's another catch. The product is extremely hygroscopic. In fact, we've never seen anything absorb water from the air so quickly. It's remarkable. Within a couple of minutes we've got a solution forming just from atmospheric moisture. We're not too sure how sensitive the vanillin reaction is to moisture, but we're betting it's not going to help at all. So we're going to get the slushy product we've got here into a small flask. And now we've got it set up with a distillation rig. We're going to heat this up again until melted and bubbling, and then use a vacuum pump to try to get as much of the water out as possible. We left it going with strong heat and the water slowly evaporating off for 3 hours. Okay, here we go. There's still probably some moisture in here, but it's as good as it's going to get. Let's seal it up and cool down. And here we go. On cooling, the liquid crystallizes to form a mass in the flask. This time there's no obvious liquid component at all, and the contents are relatively solid rather than slushy. Okay, well, we're not going to get any better, so let's get on with the next step and see if this can be used to demethylate vanillin. Here's our vanillin. This is 9.6 grams, which is a 0.25 molar ratio compared to the pyridine we started with. Let's get this into the flask along with the crystallized pyridine hydrochloride. Okay, and now a stir bar. What we're going to do now is heat the mixture on reflux for a few hours and see what happens. We'll get the heat up to a fairly high temperature. On the hot plate the setting is 250 degrees C, so probably about 180 to 200 degrees in the actual reaction mixture. We've got a calcium chloride drying tube on top of the condenser to stop moisture from getting in. Pretty soon the mixture starts to melt. And as all the vanillin went into solution, we can see a slight color change beginning to happen to a kind of honey color. Over 2 hours this then turned a more golden color, and then finally brown. At this point we realized that there is actually some pyridine being formed in the reaction flask, which is a very good sign, as this is potentially a product of the hydrogen chloride in the pyridine starting salt being somehow used up and converted into methyl chloride and the demethylated aldehyde. So we temporarily removed from the heat, and then rearranged the apparatus to allow us to distill any volatile components from the reaction mixture. And let's use a bit of vacuum to see if we can coax these off a bit faster. We kept this going for a further 2 hours at the same heating level. There was a very slow distillation of liquid over this time. The reaction mixture darkened a bit more during this time to a dark brown color, as you can see. Okay, 2 hours up. Let's first check out the distillate. We've got a few mils of watery distillate but with a very strong pyridine aroma. And here's our reaction mixture. We allowed this to cool right down and then chilled it. Interestingly, this time on chilling the mixture doesn't crystallize, it just forms the syrupy liquid. Okay, to work this up we're going to start by trying to remove the vanillin, which should be soluble in an organic solvent. First we'll add 50 ml of water to the reaction mixture to dilute it down. And now we'll adjust the pH to make sure it's strongly acid using hydrochloric acid. This should keep all our excess pyridine in aqueous solution as the hydrochloride salt. Strongly acidic now, so this should hopefully work. We get the reaction mixture into a separating funnel. And now we're going to extract this using dichloromethane. We'll use 30 ml to start with, and then follow up with another 30 ml. We shake really thoroughly for a good few minutes. Then allow to separate completely. The bottom layer is DCM, so we separate this off. And then repeat with the second portion of 30 ml of dichloromethane. We then drained off the aqueous layer into a separate flask. So here we go. DCM extracts on the left, and aqueous layer on the right, both a brown color. Let's deal with the DCM solution first. In theory this contains unreacted vanillin, and the solution certainly smells very strongly of vanillin. So we set up to evaporate off the DCM on a hot plate. Use ventilation for this as DCM vapor is toxic. And here we go. The dry solid remaining in the beaker, which is a yellowish color, but certainly smells as though it contains a very high amount of vanillin. We've recovered 6.7 grams of solid here, and if this is close to pure vanillin then that leaves us with 2.9 grams of our starting material unaccounted for at this stage. So now back to our aqueous solution. We did some research and found that pyridine hydrochloride isn't soluble in ether, but our potential product is. So let's try this to see if it's a remotely viable way of getting the product out. Let's get our aqueous solution into the separating funnel. And here's 25 ml of diethyl ether. We gave the mixture a very thorough shake for a few minutes and then allowed to settle. Let's remove the aqueous layer temporarily. And now let's drain off our ether layer. We repeated the extraction process, putting the aqueous layer back into separating funnel and then extracting with another 25 ml of diethyl ether. Let's combine the ether extracts. So here's our ether solution. A slight yellow color, so something has gone into solution. Now we'll place this into a beaker and reduce it down. Be very careful if you do this because ether vapor can be explosive. Use really good ventilation and make sure there are no hot objects or ignition sources around. We end up with the amber-colored liquid in the bottom of the beaker. And on cooling this starts to crystallize into a light brown solid. It's got a faint vanillin aroma, but not much of one. Interestingly, it doesn't have a strong unique aroma of its own. Okay, well, we've got something from the ether solution. 0.8 grams of light brown solid melting at about 150 degrees C. We don't have an easy way to verify it, but it seems to be crude protocatechualdehyde. It's very similar to the product we got from a previous experiment using aluminium chloride and pyridine with vanillin. The yield is below 10%, but it's possible that our extraction method from the reaction mixture wasn't that efficient. We might have lost a fair bit of potential product in the DCM extraction as well. But this is crazily enough comparable to the best yield we've got from any other method to date. And as a test, this experiment suggests that there might be hope in this method. The reaction is going to take a long time though, and getting the pyridine hydrochloride dry is very difficult. So we may have another go in the future and play with this a bit. There is a reference to doing the reaction in a microwave, but we don't see this as viable given that reflux then becomes extremely difficult without complex equipment. And we don't want a microwave full of pyridine vapor. So stay tuned and we'll report back if we have any success improving this.